So hello Year 12 and welcome to the third lesson in the topic 13b entropy. One more lesson after this. This is going to be a short video lesson because I want you to really put some practice into churning through those entropy questions, and so hopefully you'll have about 40 or 45 minutes after this video to go away and put into practice what you learn. There's not going to be much new learning this lesson. We're just going to look at Gibbs Free Energy. So the spec points that are covered here are just these. Know the balance between the entropy change and the enthalpy change determines the feasibility of a reaction, represented by this very famous equation, delta G is delta H minus T delta S system, and be able to use the equation delta H equals delta G equals delta H minus T delta S to predict whether a reaction is feasible and determine the temperature at which a reaction is feasible. And if that sounds rather familiar, it's because the Gibbs free energy is just a quick way to find the total entropy change. In other words, it's just another way of working out delta S total or delta S universe. The reason we prefer Gibbs free energy, other than it's a bit quicker to work out, is that delta G is related to the equilibrium constant K. And next lesson we'll look at how we can relate these and say how far a reaction will go to products. Not just will it go to products, but if so, how far it will go to products. Again, just to remind you, entropy is a measurement of the amount of disorder. So this Y has very high entropy, very disordered. This E over here has low entropy because it's very ordered. You should be familiar and happy with that now. And we looked at the second law of thermodynamics. In a spontaneous process, the entropy change of the universe always increases. So even if the entropy change of the system is negative, provided the entropy change of the surroundings is very positive, then the entropy change of the universe will be positive and the reaction will be spontaneous. And we looked at how to calculate the entropy change of the system, that it's the entropy of the products minus the entropy of the reactants. So for magnesium and oxygen going to magnesium oxide, entropy of the products minus the entropy of the reactants, and that gave us a negative number, joules per mole per Kelvin, telling us that the entropy of the system decreased. However, we also saw how to calculate the entropy change of the surroundings using minus delta H over T. Despite me flagging this up to you and saying it was crucial, many of you during your quiz questions were forgetting to convert delta H into joules, and therefore you were getting very small numbers for delta S surroundings and very wrong numbers for delta S universe. We must put delta H into joules, and once we've done that, we calculated the entropy change of the surroundings as a nice big positive number. Because this reaction was exothermic, it was releasing heat, lots more energy in the surroundings, lots more disorder. And when we compared the two numbers, that the entropy change total was system plus surroundings, we saw that the big entropy increase of the surroundings vastly outweighed the small entropy decrease of the system. So we got a nice big positive number, so the reaction was spontaneous. The standard molar entropy at 298 K for 1 mole chlorine molecules is plus 165 joule per mole per Kelvin. Use this and appropriate values from your data book to calculate the standard entropy change of the system. Although you will not be given a data book, a lot of the questions do rely on you looking up values from a data book because they're from the old spec, and therefore you do need to get used to this. So let's look it up. Magnesium would be found in the elements section. So magnesium here, entropy 32.7. So magnesium plus 32.7. Chlorine, we're told, is plus 165. And magnesium chloride we would find in the thermodynamic and chemical data for inorganic compounds, 89.6 there. So 89.6. So what is delta S system? Well, that equals products 89.6 minus reactants 32.7 plus 165, and that equals minus 108.1 joules per Kelvin per mole. There's a decrease in entropy. And why would we expect that? Well, a gas has a lot of disorder. So if you wanted, you could talk about the fact that there's free rotation and translation, more options for movement. And in this reaction, we are going from a gas to a solid. So we would expect a decrease in entropy. We said last time that temperature was very important. The entropy change of the surroundings is the enthalpy change divided by the temperature. And this means that enthalpy changes have a much bigger effect at lower temperatures. And this can change whether or not a reaction is spontaneous. And again, don't learn this table, understand this table, be able to replicate this table. If your entropy change of the system and surroundings are positive, your entropy change of the universe will always be positive and the reaction will always be feasible. It might not go for reasons that you'll learn next lesson, but it's always possible. If your entropy change of the system is negative and the surroundings is negative, your reaction is never feasible. You will never be able to make this go without a huge input of energy, continual input. If the system gains entropy but the surroundings loses entropy, that's negative, we want this to be a small number, and that happens at high temperatures. So that's why it's feasible at high temperatures. But if the entropy change of the system is negative and the surroundings are positive, then we want this to be a big number if it's going to be spontaneous, so it can outweigh that, and that happens at low temperatures, and that's why these are feasible at low temperatures. So here's an example. Show this reaction is feasible at 298 Kelvin by calculating deltaS total in joules per Kelvin per mole, giving your answer to an appropriate number of significant figures. 5 marks. Okay, deltaS system is products minus reactants, so that is 2 times 193 minus reactants, which are 192 plus 3 times 131. Notice all these numbers are positive, so that's quite nice and easy, and that is minus 199 joules per Kelvin per mole. deltaS surroundings is minus deltaH over T, remembering to put deltaH into joules, so that's minus 92,000 divided by the temperature, which is 298, and that gives us an answer of plus 309 joules per Kelvin per mole. So therefore deltaS total, which is the sum of those, is minus 199 plus 309, which equals plus 110 joules per Kelvin per mole. In other words, it is spontaneous. Explain what happens to the feasibility of this reaction as the temperature is raised. Okay, as the temperature goes up, deltaS surroundings becomes less positive, becomes a smaller number. Therefore, deltaS total becomes less positive. In other words, it becomes less feasible. And although you probably don't need to write this, eventually deltaS total becomes negative. In other words, the reaction stops being spontaneous. You did a lot about the Haber process at GCSE, and I just want you to compare this idea to Le Chatelier. Because what you are explaining is why the yield goes down as the temperature goes up. In fact, what we are explaining here is Le Chatelier's principle. So now we get to the new bit of learning, Gibbs Free Energy. And this guy, William Gibbs, originally called it available energy. And what he described it as was the greatest amount of mechanical work that can be extracted from a closed system at constant temperature and pressure. But actually, Gibbs Free Energy is just a way to tot up bond energy and entropy in one number. And you'll see it's very, very similar to the idea of deltaS universe. So Gibbs Free Energy is an easier way and a more useful way of calculating the entropy change of the universe. So we know that deltaS total is deltaS system plus deltaS surroundings. And we know that deltaS surroundings can be replaced by minus deltaH over T. So what we do is we multiply everything by the temperature. T deltaS total is T deltaS system minus deltaH. And then we multiply through by minus 1. So minus T deltaS total equals minus equals deltaH minus T deltaS system. And the key equation is this one, delta G equals deltaH minus T deltaS system. And all delta G is minus T deltaS total. So it's very, very similar to the entropy change of the universe. And this delta G is the change in Gibbs free energy. Now, we know that a process is spontaneous or feasible if deltaS total is greater than 0. In other words, if this bit is a positive number. But because of that minus sign there, that means that a spontaneous process must have delta G less than 0. Don't get caught out by it. In a spontaneous process, the entropy change of the universe must be greater than 0, but Gibbs free energy must be less than 0. So here's the equation. Delta G is deltaH minus T deltaS. Now annoyingly, for some, free energy is almost always given in kilojoules per mole. That means the units for deltaH are fine, but our units for entropy are not. So we need to convert entropy from joules to kilojoules by dividing by 1,000. In other words, if you're trying to calculate deltaS total, you need to convert deltaH from kilojoules to joules. But if you're calculating delta G, you need to calculate deltaS system and change that from joules to kilojoules. Catches loads of students out, but you've just got to do this, and you've just got to be careful what units you're working in and what units you're working to. The question will tell you, the table will tell you, but if you're one of those students who doesn't normally pay attention to units, you will come unstuck. You've got to be careful here. In the same way that when we do PV equals nRT, we endlessly say the volume must be in meters cubed, and about half of you neglect that every single time. You're going to be those people who don't get these units right. So let's do an example here. Calculate deltaS. Well, deltaS system is products minus reactants. So products 2 times 28 plus 3 times 198 for the CO. And look at how big the entropy is for carbon monoxide, because it's a gas, 198 joules per Kelvin per mole. Minus aluminium oxide, 51, plus 3 times the entropy of carbon, which is 6. And look at that tiny number there. And that's because graphite, the atoms have so little availability for vibration. They have so little entropy, it's a tiny number. And that gives us plus 581 joules per Kelvin per mole. And not surprisingly, it's a positive number. We're forming 3 moles of gas. Calculate deltaH. deltaH system, again, products minus reactants. So 3 times minus 111 minus 1669. Now, we're helped by the fact that these are elements and they don't have an enthalpy of formation, but we've got minus minuses and plus minuses, and you're more likely to make a sign error with deltaH. And that works out at plus 1336 kilojoules per mole. Again, notice this is in joules, this is in kilojoules. Finally, calculate deltaG. deltaG equals deltaH minus T deltaS. deltaH is plus 1336 minus the temperature 298 times by the entropy change plus 581, but that must be converted into kilojoules, so divide that by 1000 and we get the answer of plus 1163 kilojoules per mole. In other words, this reaction is not spontaneous. Okay, it's a positive number, and unlike entropy, deltaG needs to be negative. And we shouldn't be surprised with this. Look at this. Carbon taking oxygen from aluminium. We know from our reactivity series this is very, very unlikely. Calculate the temperature that this reaction will be feasible. Just like before, deltaS universe was 0 at the point at which it stopped or started being spontaneous. And because deltaS universe is minus T, because deltaG is minus T deltaS universe, when that's 0, so is that. So again, we know the point at which the reaction is going to be spontaneous because deltaG equals 0. And that equals deltaH minus T deltaS. So the temperature is deltaH over deltaS, which equals plus 1336 kilojoules per mole divided by 581 joules per Kelvin per mole. So we need to make sure they're in the same units. So 1336,000 divided by 581, and that gives a temperature of 2299 Kelvin. We've seen this one before. The only difference here, show this reaction is feasible at 298 K by calculating deltaG in kilojoules per mole. Again, you're given an indication of what units you need to use. Give your answer to an appropriate number of significant figures. Right, well, we calculated earlier that deltaS system is minus 199 joules per Kelvin per mole. So we can just from that use deltaG equals deltaH minus T deltaS, which equals minus 92 minus 298 times by, don't forget to put the entropy into kilojoules, minus 199 over 1000 minus 33 kilojoules per mole. And because this is a negative number, that is spontaneous. Explain in terms of entropy why this reaction is not feasible at very, very high temperatures. Well, that's because deltaS system is negative at high temps. Therefore, the T deltaS term is more positive than deltaH is negative. So the minus T deltaS term, I should say, is more positive than deltaH is negative. so delta G is a positive number at very high temperatures. And again, link that idea to Le Chatelier, higher temperatures, so less spontaneous. Magnesium carbonate is a white solid that occurs in nature as the minimal magnesite. Magnesite decomposes to the oxide at temperatures above 540 degrees C. We're at 800, so it's a spontaneous reaction, so delta G must be negative. And we can see clearly we're generating a gas here, so the entropy change of the system must be positive. In other words, it must be C. Calculate delta G reaction at 298 K for the thermal decomposition of calcium carbonate from the following data. So delta S system is products minus reactants, so 214 plus 39.7 minus 92.9, again all positive numbers, nice and easy to calculate, which is plus 160.8 joules per Kelvin per mole. Delta H system is again products minus reactants, so minus 635 plus minus 394 minus 1207. Lots of opportunity for you to make a mistake there, and that equals plus 178 kilojoules per mole. So moving up here, delta G equals delta H minus T delta S, which equals plus 178 minus 298 times by the entropy plus 160.8 over 1,000. We've got to convert that into kilojoules, and that equals plus 130 kilojoules per mole. This is a positive number, so it's not spontaneous. And again, that's what we were expecting from the fact that we know that calcium carbonate does not decompose at room temperature. Two questions for you to go and have a think about, and then I'll flash the answers up. You've got a reaction here. You're given the delta H for the delta H system. You're given the delta S system. Calculate delta G at 400 Kelvin and at 600 Kelvin. Comment on the feasibility of the reaction at these temperatures. What is the minimum temperature you would have to use? And finally, another question for you to have a go, and I'll flash the answers below. Magnesium carbonate and barium carbonate both decompose on heating according to that equation. Calculate delta H and delta S system for both reactions. Use these values to calculate delta G at 900 Kelvin for both reactions, which, if either of the carbonates, will decompose on heating to 900 Kelvin, and calculate the minimum temperature needed to decompose each carbonate. Very straightforward. Have a go at that. Right, now what you need to do for the rest of the lesson is I'm putting a worksheet on. It's got about 45 marks of questions. Have a go at those. Sometimes you're calculating delta S total, joules per Kelvin per mole. Sometimes you're calculating delta G, kilojoules per mole. Remember, delta S total positive for a spontaneous reaction, delta G negative for a spontaneous reaction. I'll be giving you the answers to those towards the end of the week, when we'll be looking at our final few spec points and throwing in equilibrium constants. See you then.